There we go. Okay, from last week, we kind of left off talking about inflection points and concavity, right? And so that's sort of our new topic that we're adding. Essentially, the way I'd like you to think about this is we're adding a row to the tables, and we're just interpreting what that row means in terms of the graph. So a good definition of an inflection point is a point on the graph of a function that has a tangent line where the concavity changes. Okay, so we're looking for places where the concavity is changing. First year calculus classes, seldom are we going to run into any weird problems where we have to really kind of look closely at this definition. In almost every case in a first year calculus class, that's going to be at a place that makes sense. It's going to be either a place where the second derivative is either equal to 0 or undefined, and just like with the first derivative, right? We're looking for transitions in sign, just like we did for the first derivative. We know a peak or relative max is a transition in sign, and so is a relative minimum for the first derivative. There's an analogous relationship for inflection points in the second derivative. So let's just warm up a little bit with maybe a graph question. Okay, so this is kind of a 3.4 practice 1 type problem. So I know it's not to the right, it's below, but you get the idea. Match the function with its first derivative and its second derivative. Well, instead of doing that, let's just sketch graphs of the first and second derivatives for this function. Okay, so give me one place, give me a point on here by show of hands. So raise your hand. Can you tell me one place where you could definitely identify a place on the first derivative that coincides with this graph? Oh, where's one?
I'd say 0, 0
is a place where the first derivative has a value of 0. Okay, so we're saying that this is the function, so we'll call this f. Then the first derivative, because we've got a horizontal tangent line right there, right, we know we have to have a 0 value of the first derivative, right? To the left of that, what's going to be the trend? The derivative's getting more and more negative the further to the left we go, right? So to the left, does it make sense that it would look something like that, maybe? And I don't know, I mean, should it be that steep, or who knows? I mean, we're just trying to get an idea of what the basic shape is. To the right of that, it's getting more negative too, isn't it? Right? If we scoot over, clear over to the right, we're going to see that we get a pretty negative slope, and down here it's even more negative. So maybe something like that for f prime. Okay, so then where is a place on the second derivative where we know its value? 0, 0 again, right? Because now we see that the first derivative has a horizontal tangent in 0, so the second derivative must also have a value of 0 there, right? And the trend is, as it go left, what's happening?
It's more positive.
More positive. If I go clear over here, we're seeing much more positive, large positive values for the slope. So this one's going to go maybe like that to the right, increasingly negative. Okay, something like that. So before we go away from this, can we make the connection? Can we just skip the middleman? Can we skip the red graph and go right from the blue graph to the green graph? Right? So think what so we're jumping right from f to f double prime. So remind me again, it's been a little while. A positive second derivative tells you what about the curve, the shape of the curve. Like, okay, it's the right idea, so I think that's supposed to mean concavity, right? But if it's positive, it's going to be concave up or down? Up, so it'd be kind of more like that, right? So it's bowl-shaped up. If it's negative, it's going to be bowl-shaped down, right? Concave down. So then over here, we can see that all the tangent lines to the blue curve up here would sit below the curve, right? So it's concave up. So we can see that makes sense, doesn't it? Every place to the left of that point right there, the concavity of the blue function is positive, right? So that matches up okay. Everything to the right of this point right here on the blue graph, the tangent lines sit above the curve. They sit on top of the curve, and so it's concave down. So that matches up pretty well. Does it make sense that this is kind of the point of transition right there, from concave up to concave down? What do we call that again? Inflection. Okay? Good. So there's the concepts. Here's the problem we did in class on Wednesday, right? So we took this function, we said that its domain, its natural domain was all reals, right? We differentiated it twice, and we did some stuff. We found the critical numbers for the first derivative. The first derivative was 0 when x equaled 0 or negative 2, right? So we added that information to our table. So at the point negative 2, we got a 0 first derivative. At the point x equals 0, we got a negative first derivative, okay? And then we did some other stuff. We differentiated again to get the second derivative, and we found a couple things. We found that the only critical number for the second derivative was at x equals negative 1, and that's where the second derivative equaled 0, right? So we added a 0 in the f double prime row that lines up with x equals negative 1. And then here's where we're able to mathematically kill two birds with one stone, so to speak, right? Now we're going to do a bunch of stuff at the same time. We're going to use the second derivative test, and I want to remind you how that works. The second derivative test, we're going to take zeros of the first derivative, critical numbers of the first derivative, and we're going to check the concavity of the function at those places, at those first derivative critical numbers. So remember, we found critical numbers of the first derivative at negative 2 and 0. Well, we evaluated, here's our work, we evaluated the sign of the second derivative at negative 2, right? At negative 2, we found that the sign of the second derivative was positive, and so now here's what I want you to fill in the blank for me. If I have a 0 first derivative, then that means we've got a horizontal tangent line, right? If I have a horizontal tangent line and I have a positive second derivative, the sum of those two concepts tells us that what do we have to have there? Does that make sense? That's got to be a relative minimum. If I have a horizontal tangent and it's concave up, then the only thing that could possibly be is a relative minimum, right? So if we have a horizontal tangent, so a 0 first derivative and a negative second derivative, then that has to be a maximum, doesn't it? Now this is a little dorky, but you can kind of think about it this way when you're making these tables. Just if you're, I mean, you can obviously probably work through the logic there, but if you're trying to think of just a quick way of remembering that when you're doing these problems, if the second derivative row is positive, then that's a happy function, right? If it's negative, the second derivative is negative, it's a sad function. So you get smiling or frowning based on that, right? Okay? So we filled in the table. We just ran out of time, but if we wanted to do a pretty accurate sketch of this, that's a lot of information there. That's essentially all the information we need, other than maybe we want to get the y values that go with these important points, just so we can anchor them on the xy plane a little better, right? So if I plug those back into my function, here's my function, well, there it is right there. So if I plug in negative 2, what am I going to get out of my function? What's that going to give us? So negative 2 cubed is negative 8 times negative 3, 24, so we're going to get 24, and then negative 2 squared is 4, right, times negative 9. So what is that? 4 times negative 9? Negative 36, and then plus 4, so what do we get? Negative 36 plus 28, so negative 8. Right? So we get the ordered pair, negative 2, negative 8. That's the exact location of that maximum, right? What about at 0? It's easy to, 0 is a pretty easy one. When x is 0, f of x is 4. Okay, so there's the exact ordered pair corresponding to the location of the maximum. And at negative 1, that's a pretty easy one too. What are we going to get? So that's going to be 3 minus 9 plus 4. What is that? Negative 2. Is that right? Yeah, it's right in there, -2. So there's our inflection point. And if we wanted to summarize this whole thing on a, this whole table real quickly, all we'd have to do is locate those points. So 0, 4, -1, -2. Let me spread that out a little bit more. I'm gonna spread the x-axis out a little bit more. -1, -2. So that's like right there. And then -2, -8. So right about there. And doesn't, now this is pretty simple. Right now we know that we're going to make this here's our maximum. Here's our maximum. There's going to be our point of inflection. So now the concavity is going to flip as we move towards this minimum. So there's a picture of our function. How about that? Okay. What other points could we add if we want to be more accurate? Well, we could find zeros, I guess, right? We could find x-intercepts if we wanted to know exactly where it's crossing the x-axis. They may or may not be important to us, though. Usually, these are going to be the places we're most interested in, right? Okay, so let's try another one. Try that. Try that. Get out your notebooks if you don't have them now. Try that one. At least get started. Okay, there's our function. Maybe we'll kind of work through this together, just so we can get through a couple more examples. What's the domain of this? All reals, good. Okay, so we've got all reals. First derivative, this is easy, it's polynomial. What do we get? Plus 4x plus 5, okay, good. While we're at it, we can come back and do some work with that, but while we're at it, let's just stay on a roll here. What's the second derivative? Okay. So how are we going to use the first derivative? What are we going to do with that?
Find zeros.
Say it again, Katie. Critical points, good. So we want to know where it's undefined, where it's equal to 0. Is it undefined anywhere? No, we're good. It's polynomial. We're good. Equal to 0. If we set that equal to 0, it looks like kind of a mess, doesn't it? If we set that equal to 0, it's not going to factor easily. In fact, I don't think it's going to factor at all. 3 times, if we tried to use bottoms up, 3 times 5 is 15. There are no numbers that multiply to 15 and add to 4, right? So we would have to use, if we weren't using technology, if you were, that'd be easy to solve, right? If we weren't using technology, we'd have to use quadratic formula, right? And we'd still end up with nothing. And let's just quick reminder of how we want to be smart about using the quadratic formula here. Right? We end up with x equals negative b plus or minus the square root of b squared minus 4 times a times c, right? All divided by 2a, so it's going to give us, what, 6 on the bottom?
We're going to get a negative square root.
Say it again.
We're going to get a negative square root.
And you can see right away that if you look at the value of the discriminant, right, the part that's under the radical, you can see immediately that's going to be negative, isn't it? Right? And so we're not looking for imaginary zeros here. We only want real zeros. our domain, we're looking at the all real numbers as our domain, right? So right away, we can see that there are no first derivative critical numbers, right? So could we possibly have any extrema? No, we can't. Right? This function can never transition from positive to negative or vice versa with the first derivative. So what that tells us, just without going any further then, what hint does that give you about the shape of this graph? Not necessarily, but it's
like a quarter function except for it doesn't come to zero. It's kind of up. It looks more linear.
okay. It's going to look sort of linear in the sense that it's going to always be increasing or always be decreasing, right? So in calculus or in math, we'd say that what this is telling us is that it's monotonic increasing or decreasing. Not that that's such an important word, but I want you to see it because you'll see it again in math. So monotonic increasing or decreasing. It's always, an ad's always walking uphill or he's always walking downhill in the entire real line, right? Okay, what about the second derivative? Are there any critical numbers for the second derivative?
-2/3.
Yeah, second derivative equals 0 when x equals, when x equals -2/3. So we do get one place where the second derivative is equal to 0. Is that guaranteed to be an inflection point? No, it's a candidate, right? We'd have to check it, okay? So we'll make our table. So we said the domain of this function is -infinity to positive infinity. No first derivative critical numbers, but we do get one second derivative critical number at -2/3. Okay? And so now what? What do you think? You just told me a little bit ago that that's a possible inflection point. How would we know?
Check the sign of the second derivative.
Okay, check the sign of the second derivative at some test points around our critical number, right? So if we try like -1 and 0, how about? So what's the sign of the second derivative at -1? Everybody agree? I get a negative result. Okay, how about at 0? Positive. So it is an inflection point, isn't it? Okay. What does this graph look like? And I guess we could figure out what's the value of the function at -2/3. I don't really feel like doing that. It's going to be, what is it as a decimal? Somebody throw that in your calculator or something real quick. Or I can put it in decimals, that'd be quicker. So f of x equals, decimals is so handy. 0.6 repeating, 3.6. And then all I got to do in decimals, right, is I can just go down to the next line and do f of 2/3.
Negative.
Oh, -2/3, there you go. Oh, I got something different. One of us is wrong. Oh, no, I'm doing the second derivative though, aren't I? No, I was doing the function. We're trying to find the coordinates of a point.
Yeah, it is the same.
Oh, okay, so that's what we want then. So that's just telling us that if we wanted to fill in, just kind of estimate, so about 1.26. All that's doing is telling us the x and y coordinates. Right? So it's giving us the coordinates of that point, which is a point of inflection, right? Okay, so if we wanted to do a quick sketch of this guy then, so if that's -1, we've got a point that's something like this. That's negative 2/3, negative 1 1/4-ish. So something like that right there maybe. There's our inflection point. And we're going from negative concavity on the left to positive concavity on the right. So what's that look like then? So this is going to be the divider. You just tell me what to draw, or you draw it. I don't care. If you want to draw it, you can. What do I get to draw at this point of, well, it's just not really a point of anything. Oh, inflection point, sorry. What's it mean if concavity is changing from negative to positive? Concave, what? Concave down. Okay, so this has got to be concave down over here to concave up. So it's going to be shedding water over here and catching water over here, right? If I wanted to be even more accurate, one thing I could do, I could go up and calculate the value of the first derivative if I want to. If I calculated a number right here, what would it be telling me? Slope. Yeah, it would just give me the slope of, that would give me the slope of the tangent to this curve, wouldn't it? Right, that might be useful. Let's just pretend we did that and we got that for our slope, right? That would be helpful because then I would know that maybe my function's going to do something like, make it a little less steep, something like that instead. So then the function would just be going kind of like that, kind of like that. That make sense? Okay. If we wanted to also find whether the function was increasing or decreasing everywhere, what would we find? Based on this picture. If we're going from, I mean, I could just plug in a test point. Whatever that number ended up being, if it's positive, it's increasing. If it's negative, it's decreasing, right? You get the idea? Okay. That makes sense? Okay. And so this is, when we get up to section 3.6, 3.5, we've already done that. That's just horizontal asymptotes and behavior. When we get up to 3.6, that's going to be the place where you guys are going to be doing paper and pencil assignments where you fill out this table and then you make a sketch based on the table. Okay. All right, let's do one more. So why did I do this one? I picked this example in particular because there were no first derivative critical numbers. Okay, so we knew, just something a little different. How about this one? There's f of x. What's f prime of x? What's that give us? Good. X cubed minus 4x minus 16x. Okay. Okay. So what about that? We haven't done a lot of work with cubic equations yet this year. Been a while since you probably have, but if I wanted to find the critical numbers of that one, it's obviously that one's going to be, it's nowhere undefined. It's a polynomial, right? But it might have zeros. How would we solve that equation? Yeah, good, good. That's the one where we're going to integrate, or not integrate. We're going to factor by parts, right? We're going to use by grouping, we call it, right? We go back a couple years. So we're going to split it down the middle. And then we want to, remember what we did with this? This is good review. So the left two terms, take out an x squared, very good. So we factor out the greatest common factor. And then we were left behind with what? then we've got this plus in the middle. And we know that over here in the second two terms, we're going to get a greatest common factor again, right? What had to be true of the leftover factor? You remember that? Must be the same. Good. Well, that's good. Yeah, you remember that stuff. That's good. Okay, so what would that mean that we're factoring out to make that happen? There you go. Okay. And then we would just, now from there, we're just going to factor out of each term. We've got two terms there separated by the orange plus sign. We're just going to factor out the common factor, which is the x minus 4, right? And then we're left with x squared plus negative 16, right? So we end up with the equation x minus 4 times x squared minus 16 equals 0. Okay, and what does x squared minus 16 factor into?
X minus 4, x plus 4.
X minus 4, x plus 4. Right. So we end up with x minus 4 squared times x plus 4 equals 0. Right? Okay, so for all that work, what that told us was that we have first derivative critical numbers at x equals what? 4 and negative 4. Okay? Let's get our second derivative. So our second derivative, then, if we scoot down here, we're just going to differentiate this in a convenient form, right? We don't want to do something crazy like have to differentiate this using a product rule. We'll just go back to where it's simple, or where it's a polynomial. So what's our second derivative going to be then? 3x squared. Okay, so we got 3x squared. Keep going.
Minus 8x.
Minus 8x. Minus 16. Okay. And then to find those zeros, we'd have to use quadratic formula, and we would get some. All they're wanting us to find here, though, in this question, do they want us to find inflection points? They don't, right? So do we really need to find critical numbers of the second derivative? Okay, everybody see that? That's an important point. No sense doing more work than you need to here, right? All they want us to do is use the second derivative test to determine whether the first derivative critical numbers are extrema, right? So we don't need to solve that. We could, but it's really not asked to, right? Okay, so now we could go ahead and make our table. I'm going to summarize this. Sure. We run out of time? Oh, my goodness. Okay, well, at least we're set up to... Okay, so my point then is just, and this is where we're probably going to run out of time, but really all we need that second derivative line for this time. Did I mess that up? All we need the second derivative line for is just to figure out if we get pluses or minuses by the first derivatives, critical numbers, right? Okay, we'll finish that one up tomorrow.
No.